So I'm Michael West. I am currently a postdoc at Johns Hopkins University. But prior to Johns Hopkins, I was doing my PhD at MIT, and then next year I will be starting my own lab at Georgia Tech in the Department of Mechanical Engineering. So if any of this research interests you, I'm definitely looking for PhD students and collaborators. So my research is motivated by what we call the paradox of human performance, which I think is really illustrated by these two videos shown here. So if you look at a lot of the state of the art of robots, you see, this nice coordinated movement, robots doing things like martial arts, dancing, flipping. But when we think about physical interaction, we don't see a lot of robots doing what we consider humans are capable of in the state of the art of physical interaction, right? Where I'm showing highlights of one of my favorite football players, Aaron Donald, who can consistently dominate 300-pound dudes and sack a quarterback, right? We're not getting robots that are capable of these capabilities just yet. And what makes this a paradox is when we think about the wetware and hardware of humans and robots, right? Humans have actuators that are an order of magnitude slower than robots. They have communication that's 6 orders of magnitude slower, feedback delays that are 2 orders of magnitude greater. And on top of that, we have this really complex system of greater than 600 joints and 200 muscles. So if we put all of these elements into a robot, we'd say this is a pretty crappy robot. Yet, when we compare human and robot performance, humans exceed that of robots. Which brings me to my research. I study human motor control, perception, and learning to try and bridge this gap between humans and robots. That is, trying to understand how humans are able to coordinate their movements, what sort of simplifying techniques they're using to be able to achieve this performance. So in essence, I use control theory, simple models, and robotics to understand human motor control, perception, and learning, and try and embed those insights from humans into robots. In my lab or in my research, we follow a human subject experiment pipeline where we'll come up with an experiment that we want to use to test a hypothesis. We'll bring people to the lab and we'll collect experimental data of their kinematics and biomechanics. We'll use simple models, namely those of dynamics and biomechanics, to model the human as they're doing this task. And we'll try and figure out what possible control inputs the central nervous system has to explain our data using control theory. And then also recently, I've been delving into trying to understand different perceptual or sensory information, how that affects how humans are building their internal models and their controllers as well. This research has a lot of applications in human-robot interaction, skill acquisition, rehabilitation, and medical robotics. And sort of drive that application home, I'll tell you how I've sort of been thinking about this problem. It starts with this concept that human ability falls on a spectrum. And if we want to sort of classify this spectrum, I would put it into 3 categories, right? Novices, which are people who are trying to learn or relearn how to use their bodies for activities of daily living. You can think of those as children and patients. Intermediate, where we have people more or less like ourselves, unimpaired adults who are capable of using our bodies for different activities of daily living, and we're able to get through the day. And then we think of experts, people who are trying to push the capabilities of their body, push the coordination of their movement, their dexterity, to be able to use their body to make a living. So you can think about musicians, surgeons, and athletes. When we define motor learning, we think about going from one domain up to the next, right? So in the novice to intermediate case, people often call that rehabilitation. You want to accelerate the rehabilitation process by adding robots. And this is a huge industry that I've done some research in and a lot of people are working in as well. This other direction, though, going from intermediate to expert, I'll define that as skill acquisition. And there's not too many robots going in this domain to try and accelerate this learning of skill acquisition. And that's a bit about what I'll talk about today, this idea of having robot coaches to accelerate skill acquisition. This is a snapshot of some of my prior work, but today I'll be talking about work in the visual perception of dynamics and then a couple of complex skill acquisition tasks I've studied, namely piano playing and robotic surgery. So before we can accelerate motor learning or accelerate skill acquisition, we want to figure out how can we quantify it. The same thing we start to think about when we think about our students in class. We want to be able to quantify their learning via grading. So my PhD, I developed this metric that I think can push us in that direction named VAF-CI, and I'll talk about that now. Before we can talk about the actual components of the metric, though, I'll introduce you to this component of human motor control, namely synergy. So if you recall the very first slide, where we talked about the complexities of humans and how we have these many joints and actuators we need to coordinate to produce movement. One of the questions becomes, how are people able to do this? And the idea is that we have synergies. We can think of this as about a subspace of control, or we're simplifying the control of many joints by controlling all of them simultaneously. The best way to sort of think about this is thinking about the human hand. When we use our hand, we rarely ever move each joint individually. Rather, we move many of them simultaneously in a gross coordinated fashion. So you can think about this first grasp, which we call a power grasp, just general opening and closing of the hand. You can grasp many objects using said power grasp, where you're moving all of your joints simultaneously in a coordinated fashion. And a second synergy would be this pinch grasp, where you can start to pinch and grasp more smaller objects. A lot of research has shown that these two synergies, or these two gross coordinated movements, account for a lot of different grasp types that humans are capable of that allow for activities of daily living. And this subspace of control, or these synergies, have been used as a method for different aspects of rehabilitation robotics, right? So when you think about prosthetic hands, these prosthetic hands aren't necessarily fully actuated. They often incorporate these couple of synergies. Also, in the rehabilitation space, oftentimes people who are trying to rehabilitate dexterity will focus on these main synergies that allow for a lot of the activities of daily living. So my metric builds upon this synergy-based analysis. So it's VAF-CI, symmetric to quantify coordination complexity or movement complexity. And it uses synergy-based analysis to quantify task complexity via the coordination structure of joint movements, which is very jargony. I'll skip through the math and just show you through the logic of how it works. So the idea is that as task complexity increases, you need more independent patterns of coordination. And this becomes, the coordination becomes less compressible into a few synergies. So to sort of think about this, when you're grasping a water bottle, you can generally do that with one gross open close movement of the hand. When you move to a task that is more acquired or more learned, like typing a keyboard, now you need to start pressing each finger individually. So if you think about on your keyboard, when you're first learning, if you wanted to press the J key with your index finger, sometimes you'd accidentally press the K key as well because that finger was coming. So all this together is what VAF-CI sort of captures. The idea, in essence, is that as task complexity increases, we can use this mathematical technique, and VAF-CI should increase, which leads to a testable hypothesis. And namely, in our lab, the testable hypothesis that I conducted was that the complexity of 3 distinct tasks can be identified using VAF-CI. So in the lab, we had people come, we measured their hand kinematics as they did these 3 different sets of tasks that we believe to be of 3 different levels of complexity, namely reach to grasp, tool use, and piano playing. So after extracting the kinematics from people's hands, they did this task, we computed our metric, and what we found was this VAF-CI metric differs for distinct tasks in a manner that's intuitive or consistent with our intuition. So again, as our metric increases, the task complexity increases between these 3 tasks. Namely, piano playing is more complex than tool use, and tool use is more complex than reach to grasp, which is again, is shown that our metric is aligned with a result that's consistent with our intuition. Another key aspect of this metric is it quantifies manipulation on the spectrum. So what's shown here on the x-axis is the different subtasks that participants did in our experiment, where RTG is reach to grasp and TU is tool use. And they're ordered in the course of increasing VAF-CI task complexity. What we see is in this middle group, some of the more dexterous tasks, namely tying a zip tie or screwing a screwdriver. And in this upper group, the piano playing tasks, which are of high complexity. And what's even more interesting is when we zoom into the piano playing tasks, what we see is on the lower end of the spectrum, first we see again this complexity of spectrum of different piano pieces that the participants played. On the lower end of the spectrum, we see a beginner piece named Bach Prelude in C major. And on the higher end of the spectrum, we see a more advanced piece named Chopin Etude 2511. So what have we shown so far? We've shown that VAF-CI can objectively quantify the continuous complexity of manipulation tasks. But why is this important? So one thing I want to start to think about is, what do experts do as they begin to master a complex task? And this led me to think that they try and make it simple. So the question I wanted to ask was, okay, can we use VAST-CI to also quantify human motor learning? That is, can we measure the simplification as people learn to do a task to become a master of a complex skill? And this led me to surgical robotics. I think surgical robotics is an ideal test bed for studying motor learning. It has a few important components. One, it's a very challenging task. It takes years to learn. But it also has a well-defined progression from novice to expert as you go from medical student to resident to fellow to attending. It also has standardized tasks and tests that enable comparisons across these different skill levels. And on top of that, because it's robotic surgery, we have continuous kinematic measurements for every instrument that the surgeons are controlling. So all this together leads to an ideal environment for testing this question of, as experts learn, do they make the task more simple? Namely, can VAST-CI quantify the learning progression in robotic surgery? So to answer this question, I turned to this open source data set called Jigsaws, which was collected about a decade ago in a collaboration between Intuitive Surgical and Johns Hopkins University, where they brought different participants of varying skill level in to do these 3 different surgical tasks: knot tying, needle passing, and suturing. And with this data set, what they had was they had independent graders view the videos of people doing this task. They didn't know who did this task. They graded the performance using their known surgical grading techniques. So now the data has been labeled with the level of skill. And also, again, because it's robotic surgery, we have the kinematic measurements of the tools, which means that I can use my VAST-CI metric to see if there's a relationship between the instrumented kinematics and the actual labeled skill. And the key question becomes, does complexity decrease as surgical skill increases? Again, do surgeons simplify as they learn to do this task? So what we found was across all 3 of these different tasks, when we look at the VAST-CI metric and compared to the global rating score, or again, the individual grader score, VAST-CI actually does decrease with skill, which says that, experts might make the task simpler as they learn to do this task. Experts might make the task simpler as they learn to do this task, which tells us that VAST-CI can quantify this simplification as people are learning this complex motor skill. So thinking about this picture again of my research, I've talked a little bit about the motor control and human skill acquisition and focus on quantifying, focus on the first step of accelerating motor learning and skill acquisition, namely quantifying learning. Now I'll pivot and talk a little bit about perceptual tasks and trying to, again, accelerate this skill acquisition in a complex perceptual task. So this research was motivated by the fact that it's from these point light animations, it's very obvious to show that people can extract latent information from visual observation of movement. From these point lights, you're able to tell that someone's walking, jumping, now climbing a set of stairs just from observing these dots on the screen move. And that's because we all have an understanding of how we would control our body to do these tasks, and we can extrapolate from how we would control our body to do these tasks and embed that into our perceptual understanding and fill in the gaps from these videos. So turning to the motor control perspective, we wanted to ask a similar question, namely, can mechanical impedance be perceived using visual observation of movement? Mechanical impedance is a relationship between motion and force. And there's a lot of literature in the motor control space that shows that this impedance is how we control our muscles to be able to do different physical interaction tasks. One way to sort of think about mechanical impedance is it's the relationship between motion and force. So in this equation here, Hooke's law, F equals Kx, you can think of it as the stiffness component. So to test this, what we did is we had participants come to the lab, they sat in front of a computer screen, and they observed this 2-link manipulator move. And then we asked them to rate the stiffness of this 2-link manipulator. And I want to highlight that this is a non-trivial task, right? Stiffness is a relationship between motion and force. From just observing a 2-link manipulator move, all you can get is motion information. You have no access to force information. So effectively, we asked our participants to solve for K with only X with no information to F, which in theory should be impossible. So to drive this home, I will do a variation of this experiment with the audience. So again, we'll ask you to observe these 2-link manipulators move, and I'll ask you which of these 2 is stiffer. So raise your hand if you think video 1 is stiffer. Raise your hand if you think video 2 is stiffer. We have a pretty shy audience. In a second, you guys will be more brave. But it was about 50-50. Those who said video one were correct. So again, in our experiment, people were generally good at this task. And what we found is, again, on the simulated joint stiffnesses of the videos that we showed to participants, we see a positive linear effect between the simulated joint stiffness and their stiffness rating. So subjects are actually generally good at this task, which says that humans can robustly visually estimate stiffness. And the way people were able to do this, I'll gloss over these results, but they're in this paper here, is that they're able to do so by drawing upon their own internal model of how they produce their own motion. So thinking about how they were moving their arm and what stiffnesses they might use to produce similar motions. And the other aspect was they used primarily path information, so namely displacement, not velocity in its derivatives. And then another key component of this was our best participant was a physical therapist. And this is really interesting when we think about this concept of humans' ability being on a spectrum, right? Physical therapists, I would call them expert perceivers. Their whole job is to observe a patient move, quantify their level of impairment, and then identify an intervention, which makes it pretty interesting that the person who had the best internal model of this task was a physical therapist. So the key question becomes, how did they build the internal model? And that's what the study of human motor perception is trying to answer. So if we have an understanding of how people perceive this model, then maybe we can improve this via some sort of automated or robotic coaching. So to take you a little bit through that example, where hopefully we'll get you guys to be a little bit braver now. So we've identified in that previous paper that the way to tell the difference in stiffness between these simulations is we're going to have you observe the elbow's range of motion of these two, and that's how much the elbow open and closes. And the one with the smaller range of motion has greater stiffness. So again, I'll ask you, which of these videos has greater stiffness? So raise your hand if you think it's video 3. Now raise your hand if you think it's video 4. So greater audience participation, and again, more of you guys are correct. And we're able to identify how to do this task and coach you how to do this task by a study of human perception. And in fact, we did this similar experiment in the lab with a talented undergrad at Johns Hopkins, Leah Wong, to answer this question of, does targeted automated coaching improve impedance perception? And what she did was she had participants do the perception of stiffness experiment, where they observed this two manipulator move, they rated its stiffness a few times, and then we had them watch an automated coaching video which told them where to look. And then we had them do the task again. And what we found was that, and we'd have them do this across 3 different participant groups, the first of which received no coaching, the second of which received coaching to tell them to look at the hand, and the third of which received the coaching that you guys just got, look at the elbow angle. And what we found across these 2 metrics that measure accuracy and precision is that this angle coaching significantly improved people's ability to do this task compared to the other 2 coaching groups. So the key takeaway is that targeted automated coaching can improve impedance perception accuracy. And I want to highlight the importance of the targeting, right? The hand coaching wasn't as effective as the elbow angle coaching. We were able to identify this from experimentation. That is, identify this from study of human perception. So just to end, what have we learned today? We said that I've talked about the use of control theory, simple models, and robotics to study human motor control, perception, and learning to help us uncover that experts progressively simplify movement coordination as a required skill. And VASCI can measure this by measuring latent coordination. And that we've shown that humans can perceive latent dynamics via visual observation of motion, which again is remarkable. They're solving that F equals KX equation with only X, no F. But we found that understanding how people are able to do this perceptual ability allows us to improve this through automation or robotics. So again, thinking about this concept of human ability falling in a spectrum, we focus a little bit on the skill acquisition. I'd say the key takeaway is that it's uncovering latent structure in human motor control and perception may provide a foundation for robotic or automated systems to both assess and accelerate human motor learning. So I just want to give a thanks to my funding, my collaborators, and I'll close with questions.
We have time for probably just one question, unfortunately, but hopefully Dr. Willis will stick around and launch to questions. Question?
Hello. Thank you for your presentation. My question is, well, first, congratulations on getting your lab in GT. And my question is related to that. So with this, I guess, preliminary research that you've done that's leading to this lab, what are you hoping to discover, or what breakthrough you're hoping to achieve through that opportunity?
Mm. So the long-term vision is having robots that automate this idea of robotic coaches that accelerate skill acquisition for complex skills. The current starting point I'm thinking is working in surgical robotics. And to truly get this automation of skill acquisition, it's really important that we understand actually how humans learn, right? And I think, a lot of aspects of AI and robotics sort of miss this point. We miss sort of the basic understanding of, if we want to use robots not to just replace humans, but to accelerate and augment humans, it's very important we understand humans. So that's pretty much the foundation of the lab. And then we're working on everything in between to getting that, the actual deployment of these robot coaches to accelerate skill acquisition.